like to welcome everyone back to the Wilson Science and Technology Forum today. I'm happy to welcome a longtime friend, Jagadeesh Moodera, who is affiliated with the MIT Physics Department. He's also a member of the Francis Bitter Magnet Lab and the Plasma Science and Fusion Center. So Jagadeesh wears a number of different hats, and we're delighted to have you with us today. He's going to speak with us about the evolution of quantum computers. And there have been breakthroughs in his laboratory at MIT on issues related to magnetic tunnel junctions and superconducting electronics, both of which are enormously important to quantum computers. It's worth recognizing that if, or maybe I should say when, quantum computers appear in the marketplace, their power demand to run artificial intelligence software is enormously less than the power demand required by classical computers. And this raises into question the huge investment that AI-oriented corporations are making today in data centers, which draw enormous amounts of power from the grid, and in some cases are looking to restart decommissioned nuclear power plants to supply their power, when it may well turn out that if quantum computers become a reality in the marketplace, they will reduce that power demand dramatically. And so it just seems to me a very interesting almost dilemma that somewhere we're going to have to recognize, and these companies are going to have to deal with. So anyway, I'm delighted to have Jagadeesh with us today. He is an expert in this area and someone that I'm delighted to have visit the Wilson Forum. Jagadeesh, the floor is yours.
Okay, very good morning. Especially I want to thank Professor Ron Tennyson. As he said, I know him for a long time. It's fun to have dinner once in a while with him and Caroline. So this is a result of that kind of interaction we have had. There are many kinds of interaction over the time. It's a pleasure. And I see when I hear all you people introducing yourself, I have actually a stellar audience here. It's amazing. Thank you so much for all of you to having come, and whether you're eating breakfast or finish your breakfast or waiting for your breakfast, it's wonderful. Okay, so what I will try to do is I'll take you through a journey, rather what we have followed over the time to using let's see. Okay, so how work in fundamental science has led to what we think is some of the major progress in information storage and communication. So in fact, it can also actually assist in developing computers of much better efficiency than what is there today. So as you can expect, our program over the years has been funded at different stages: National Science Foundation, Office of Naval Research, Army Research Office, and Air Force Office of Scientific Research. And in fact, John Templeton took the risk to actually help us in looking for the Majorana bound states. So that's where the foundation comes to picture. Now, I don't want to go through all the details of what we have, as one of the audience mentioned that is too much about. So as you can expect in basic research, we essentially follow our imagination. So we try to do various things. As we go along, we find that something else is more interesting, we follow that path, and so on. It's like almost like a random walk in some sense. Whereas, although we cover up many areas here, like electron spin transport is one of the major things we have been working for a long time, and that is termed as a spintronics. Then the other thing of interest, fundamental interest to us, is the ferromagnetic superconducting interfaces, because they're antagonists in principle, but when you combine the two together, it's an amazing amount of richness you have at the interface. So that is what drew us towards that one. That's what actually has led us to some of the progress we made in the superconducting quantum devices. That's the second part of my talk. The first part is going to be something related to spintronics. They also worked in topologically driven systems that we'll now get to talk to. In the middle of summer, I'll introduce you this Majorana bound state, how we went about finding the Majorana bound state in a gold. So as you can expect, over the years, there has been contribution from a lot of people. It's not just one man show here. So we have had about 200 high school students, undergraduates, grad students, and visiting students from various plots. And we have also had about 70 to 80 postdocs actually visiting, including Humboldt fellows. And we have had actually more than 30 visiting scientists from various parts of the world. So this is what made it very rich in this field. So we enjoyed working on that. Okay, how do we do this? So these are the kind of equipment we use. On the left side, what we have is called molecular beam epitaxy system, which essentially allows us to make a very, very controlled, clean, ultra-thin film and a combination of various materials create hybrid structures that essentially limited by your imagination, basically. So we can actually have any kind of combination of materials. That's what makes it very rich and very fertile ground to explore new phenomena. That's what we have been doing over the years. And the right side at the bottom, you see that's kind of equipment we use to measure the properties of these materials. After making them into nanostructure, either using MIT nano facilities or we have our own in-house scanning electron microscope to make the small structures. So we make devices which are very small. Here's the thin films to begin with, and then we make smaller devices. That brings us to do the measurement in this kind of magnetic transport system. This is one of the automated systems which have been in the market for the last couple of decades or more. It's extremely popular. And in the middle, you have what's called a scanning tunneling microscope. This is something which was invented in the 80s. And of course, within a short time, they got Nobel Prize for that. And what it does is it's a small scanning probe, which allows you to look at the surface. You can see the structure of the atoms, and you can even do the spectroscopy at the atomic level. This is the very, very powerful technique. There's a lot of science we can do, new science. And we have used that to especially to look for this Majorana bound state that helped us a lot. This actually can cool down to 280 millikelvin, and it has a large magnetic field, 5 Tesla, so that is needed for looking for the Majorana pair. So basically what we do is experimental work, setting the foundation for what can be used later on for either in the computing industry or in quantum computers. Okay, so let's see what we are doing. For example, electron has both a charge and a spin. When you talk about spintronics, what we are doing is using the spin part of the electrons. So basically use that to actually manipulate, to either store information or manipulate it, or you can actually transmit information. You can do any of those things. This is possible because of magnetic materials. As you see here, is a response for magnetic material as a function of magnetic field. So what we have, the vertical axis is what's called the magnetization. That's a response. And horizontal axis is the magnetic field. So these materials are so important for the last, I don't know, 68 years, and it's going to continue to be important for the next number of years, because as you bring back the field to zero, you can see this state is maintained, and you reverse the magnetic field with a finite value, and then you actually again also go back to the reverse side. Again, this value is maintained. That means this information is in the material system, which is permanent essentially. So that's what makes it extremely valuable for sensing and non-volatile memory and all these hard drives and so on and so forth. So that's what drove the industry for the last 50, 60 years very strongly. Now, to give you an idea what memory devices are those tools where we store information and are able to retrieve the information. This information has to be long-term lasting, and that means you can rely on it, and you can also put as much information as possible. That will be the most efficient memory. Now, on the right side, what we see in the top is the way the magnetic memory was in 1956. Okay, so it took 4 men and a truck to transport 5 megabits of memory, equivalent to one song in an iPod nowadays. Now compare that to what is currently available, 2025. So we have a disk which is the size of the wallet, which can store 6 million times more information than what this was able to do in the past. So can you imagine this? To have this kind of memory, those days we need to have essentially 6 million trucks or 6 million cartoons as shown here. So we have come a long way, as you can see here. 30 million or 30 terabytes memory is a very large memory. So given that one, we can actually store a lot of information. And in fact, even that is not enough these days with the onset of the artificial intelligence. There's huge demand for that. This is a picture of one of those. Can you see the top of the slide, Ron? There's some coverage here.
Yes, we're fine.
Okay, so anyway, this is a typical picture of a data center. And you can imagine there are probably hundreds of them all over the world. So this room is a very big room. As you can see, this could be about 30 meters on each side. So there are so many racks here. This, of course, stores a lot of information. But this kind of room needs a lot of energy to keep it cold. I think they keep it at 10, 15 degrees C or something like that. So the huge amount of power is needed. So this is not going to be sustainable in the future. As you can imagine, as AI starts growing faster and faster, then the amount of storage you need goes exponentially. It's a problem. Now, what actually drove the magnetic materials to show this behavior is the following. If we take a paramagnetic material such as copper, gold, platinum, what we have is the conduction electron, the electrons that participate in the transport process. They have the same number of upspin and downspin electrons. That means there is no polarization. Polarization is a degree of one of them being larger than the other one. Now, if you take the middle one, what you have is upspin electrons have much more than the downspin electron. That means this is the uneven distribution of these electrons. So as a result of that, you can have what's called the spin polarization of these conduction electrons, about 40%. This is standard value for most of these standard ferromagnetic materials, such as nickel, copper, iron, and the alloys, and so on and so forth. So that means spin up is not the same as spin down, and that net change is given by this percentage. Now, there are also new materials, which have been around since the last 10, 15 years. And it's not so easy to make those things. They'll have their own limitations, where there are no spins at all in one direction. Only one like upspin electrons are there at the Fermi level. That means all the electrons participate in the transport process. They're all spin polarized in one direction. As you say, this is 100% spin polarization. So these conduction electron spin polarization is what driving all these things, whether you're talking about sensors, magnetic random access memory, logic, and so on and so forth. That is the crux of this data storage. Okay, so our work is usually pertains to these kind of materials, wherein we can actually determine the spin polarization and also see what affects them. That's important to know. If you want to make a device, you want to know what actually is good or what is not good. This is what we do. So let's talk about the beginning of this, what's called the magnetic tunnel junction. This is called MTJ. I'll use this term extensively in my talk. So keep in mind that this magnetic tunnel junction, which means you have magnets on both sides of this tunnel junction. Tunnel junction is shown as here. So Paul Tedrow and Robert Mesavi, they were my supervisors one time, and they both are retired. In fact, unfortunately, Bob Mesavi is not around anymore. Paul Tedrow is there. He lives in Lexington. They discovered this phenomenon of spin polarized tunneling. So they were working at the magnet lab. They found that ultra-thin superconductor can be used to detect the degree of polarization in a ferromagnet. That was a discovery. That was a major discovery. That's the starting point, what's called a spin polarized tunneling field. Now, they also showed that spin is conserved in the tunneling process. Now, let's go back to see what is tunneling. For example, this is the schematic view of what's called the quantum tunneling. If you bring two electrodes together, just about 1 to 2 nanometers away from each other, current can flow from one electrode to the other electrode. This is completely quantum phenomena. The wave nature of the electrons is what gives rise to this behavior. So as a result of that, because of this exponential dependence of this tunneling current, so thickness of the barrier and also height of the barrier, very, very important, as you can see here in this equation. So one has to control this insulator extremely carefully. That's what took a long time to start making these things useful for application. So that's a typical picture schematic of what a tunnel junction, real one, looks like. We have one electrode, the red one, and they have a thin insulator shown by yellow, and then your top electrode is shown with orange. You just connect the current and voltage electrodes to a thing, and then you can measure the characteristic. This is what's called a tunneling spectroscopy. In fact, Gaver was the first one to show the power of this tunneling when he actually did the tunneling spectroscopy using superconductors. He was the one to first to show that the energy gap of a superconductor can be determined by tunneling. So that actually gave him Nobel Prize 10 years later. So this is a very, very powerful technique. There are lots of work has been done. There are probably tens and thousands of papers on tunneling. So in Pacific Tedro used aluminum superconductor and nickel is a ferromagnet. That's what they used to show this spin polarized tunneling principle. Now, this is the kind of equipment they used. Earlier, you saw what the fancy equipment which is currently being used. Now, that is the kind of equipment they used at that time. This is a thin film deposition system again. They put together, in fact, the story is that a lot of parts in this one were actually thrown away by various national labs and the Air Force lab, this and that, Lincoln lab, Raytheon lab, and all that. They put together all these things, they made this system. This is one of the systems which is really magical, what we call a system 3, which has produced the number of breakthroughs is amazing. So I tell my postdoc students, it's not the equipment, it is your mind which can actually produce new breakthroughs. So this allows us to make thin films of various materials and make your multi-layer system and so on and so forth. They made these kind of things. They made junctions of this kind. They use this kind of, again, home-built system, which can go down to 0.4 Kelvin, which is 400 millikelvin, and you can apply a large magnetic field to study the spin polarized tunneling spectroscopy. So what I want to show you here is these two equipment are essentially built in the 1960s. They both are still operating. So now we come to the magnetic tunnel junction, actually magnetic tunnel junction. So based on what Mazevin Tato showed, that the spin is conserved in the tunneling process, and you can also have spin polarization coming from magnetic electrodes. What Michel Juliet, he was a PhD student at the time in France, and he came up with this model. If you put a ferromagnet, two ferromagnets separated by a thin insulator, in his case, he used amorphous germanium, which was not the best choice at the time. So anyway, he came up with this model that the tunnel magnetoresistance is something which can be actually determined by changing the magnetization, changing the resistance of the system when you go from parallel state to anti-parallel state. That is what the TMR is about. This is actually proportional to the spin polarization. As you see here, P1 and P2 are the polarization of this magnetic electrode and that magnetic electrode. Naturally, one expects to see a very large TMR depending on the value of P, which is very high. Now, let me tell you the basic principle of this TMR. Now, this is a two-band structure. In other words, this is the way the electrons are distributed in a ferromagnet. Now, you can see here, this is magnetically pointing, say, upwards, and this is also magnetically pointing upwards. That means the number of spin-up electrons are very large here, and that can go into this one, which is also having very large empty states. That means the current can flow very easily. That means a large current shown by the size of the arrow here. But the minority spins also do the same thing because the spin is conserved. Nothing happens to the orientation spin. So as a result of that, this is preferred. Now, if you reverse the magnetization of one of the electrode, that means you make them anti-parallel to each other. Then what happens is this large number of carriers here don't find enough place to go here, the current drops. And same thing the other one too. You have less number of minority spins, but they have lots of states here. Once again, current flow is not enough. So as a result of between these two states, by just changing the magnetization being parallel to anti-parallel, you can have a very large tunnel magnetoresistance. So this was 1975, as you can see here. That's when Julia came up with this model. And there are a lot of attempts between 1975 to 1994. Everybody wants to come up with this simple model and realize this possibility of having a very large TMR, but that didn't happen. Until 1995, 94, 95, when we set out to do this, we wanted to take up this task. We were actually doing it in some way, but then we really wanted to seriously get into this. So that time I had this story is this. That time I had Lisa Kinder working with me. She was a high school summer student. Then I came from a conference. I told, okay, let's try this particular thing, like to do the MTJ, look for the TMR. Then she was excited about it. She was only 16 years old. She didn't care what the risk factor. I told her, no, in 4 weeks, we will not have much result. But she didn't care. She said, oh, I want to see this. I want to do this. So then we set out to do this kind of structure. And in fact, we were able to actually produce a very large TMR. by carefully controlling the insulator thickness and also the cleanliness of the interfaces. This is done all in situ, one growth. So we were able to realize what was expected essentially 30 years ago or 20 years ago, what's called the TMR in between two magnetic electrodes. So what we have here is the resistance of this kind of structure that may change in the current, but in going from parallel state to anti-parallel state. In parallel state, you have large current, that means the resistance is low for a given voltage. And then you reverse the magnetization, you have anti-parallel state, whether you in the positive side or negative side, use the same thing, you have large resistance. Now, on the other side again, once you align them parallel once more, you have a low resistance. That means the current is much larger. So this is what we discovered in 1995. At the same time, we also found that if you fix one of the magnetization, it doesn't change very easily. But in this case, you see one of them changes here, other one changes here. So both can be changed depending on the applied magnetic field. Now we fixed one of them, and we found that by toggling the second magnetization, going from parallel to anti-parallel state, you can have this kind of box-like structure. So what you have here is a zero magnetic field. If you go to high field, come back to zero field, you have a low resistance state maintained. Now you go in the reverse direction, make them anti-parallel, the resistance is high now. You just turn off the magnetic field, you actually reach this point. So these 2 points are the most important one for creating what's called the magnetic random access memory. It's a non-volatile memory. This is what is driving the field now. So in zero magnetic field, you have two magnetic states, which can be retained even if you take out power, everything off, you come back after 10 years, 20 years, you still have these states maintained. This is what the non-volatile memory is about. So at that time, we were able to see about 42%. This is actually done at 77 Kelvin, room temperature a little lower. So at any rate, we were able to show two things. One is you can see this memory effect. Other one, you can actually realize this TMR using magnetic electrode. That was starting point of the field of the way it drove itself. So you can see Dr. Mezavi is also involved in that in the project. You can see Dr. Mezavi is an avid photographer actually. So anyway, now then what happened? Few years later, it turned out that if you instead of having a polycrystalline or a disordered system, if you're able to
Did we lose him, or is it just me?
No, something happened. Jagadeesh, we lost you. Oh.
It's the electrons in his computer.
Yeah, must be. We need qubits.
Looks like the field reversed.
Let's see if I can call.
Cell phone. Gotta call him on his cell phone. There he is.
I had to go back and share again.
We lost him completely. Oh, here we go.
Okay, it's okay now?
Yeah, what happened?
I don't know. When did you lose? I don't know.
Okay, I'm glad you're back. I was just trying to call you. Okay, good.
Okay. So maybe previous one you missed, previous one. But it's not moving.
No, it looks like it's working. There you go.
Okay, so that was theory prediction. We can have a very large TMR. And it was experimentally realized by two groups. One is the group from Japan, Yuasa et al., and another one is Stuart Parkin from IBM here. They were able to realize this kind of ordered structure, and they could actually see 200% TMR. That's a major, major break. As you can see here, TMR is hovering around 50 to 80% with aluminum oxide. But the moment MgO came along, the picture, you can see a huge increase. So that is actually another huge accelerating point for developing memory and hard drives. Now, this is a typical hard drive in a computer. I'm talking about desktop computers. Nowadays, laptops have solid state memories most of the time. And this is what the actual memory looks like. There's a disk here, which rotates anywhere from about 7,000 RPM to 15,000 RPM. And on the top of that, you see there's an arm. At the tip of the arm is where the sensor is. That is where the magnetic tunnel junction is. So this was they were able to actually use the magnetic tunnel junction in this kind of structure. So able to actually see extremely small signal and very close. And they were able to utilize in the read head as in the hard drives. That's 2004. Just imagine within about 8-9 years, they were able to develop. They used, of course, titanium oxide as an insulating barrier between the two magnetic electrodes. So at the same time, they also started bringing up what's called the magnetic random access memory. That's a company called Freescale, and now it's, I think, Everspin. So they also started bringing in other words, you can maintain two resistance states in the system by actually tweaking the magnetic field using an electrode, sending a current pulse through this wire across. This is a copper wire. Then you can produce a magnetic field that can change the magnetization orientation of this one. So they can actually toggle the memory state. So hard disks now have reached greater than 10 terabytes. As you can see that you can buy in the market around $200 for 10 terabyte memory. Imagine when the one time we had to get like 20 megabyte, which is 1 million times smaller, then it would cost us almost $500. Now that's actually the more cross-sectional view of this hard drive. I don't think I want to go into too much detail. All I want to say is magnetic tunnel junctions are so small and have such a fantastic signal that way they are able to see extremely small changes, and at the same time very fantastic spatial resolution they have. And that's the right head. So a disk is something like this, rotating disk. As you can see here, the grains made up of grains, very thin, on the order of actually 10 or 20 nanometers thickness. So whole thing is extremely thin, the disk on the disk, each of these materials. Now this read head and the right head, they're spinning. I mean, this disk is spinning, these things actually floating above. The distance between this arm, that's this read head arm, and the media is only about 5 nanometers, 3 to 5 nanometers. Can you imagine how close it is? So how perfect the disk has to be, absolutely aligned. And that's when we say my disk has crashed, means this read head has went and hit the surface. It doesn't take much to hit the surface. So you can see how delicate it is, the whole thing is. Okay, now let's switch to magnetic random access memory. So as I mentioned to you, this is the picture I showed you earlier. Maybe there's a time when the system was down. So we have two resistance state, one is high and the one is low. This is the what's called the non-volatile memory. We are able to maintain this one. And what they have done is they've gone a long way. They are able to actually have the magnetic random access memory or this MTG structure in compatibility with semiconductor processing. They have CMOS here, and they have created the CMOS transistor here, right here, which actually drives the current through the system, and you have an MTJ. So this current actually is able to rotate the magnetization from one direction to other direction, which means you don't need a magnetic field to switch the magnetization. They use what's called a spin transfer torque. That's what they use here. Nowadays, they're also working on what's called a spin-orbit torque. These are the things which are driving the field into a very high level of density. So these disks don't need a magnetic field. They can be completely operated in an electrical way. This is what is expected for the future, any kind of device application for these things. So right now, as of today, probably on the order of 64 gigabit chip, we can see magnetic random access memory, which is non-volatile. So that means it uses less power. And I think I can't see myself this one top line. How do you get there? Yeah. See, this is uses low energy, is compact, fast, and unlimited endurance. This is the largest endurance. You can cycle it 10 to the 15 times, 10 to the power 15 times. Still, it's just fine. It works fine. So that's what makes it extremely important. So that's a development that has been going on in the last maybe 10 years. Now it's extremely high density is being reached. They're looking for 128 gigabyte chips and all that. Most of the time, it's going to be likely this one, spin-orbit torque driven switching. So why sometimes freezes? Okay, so that's the principle of spin transfer torque. What we have is a magnetized system which actually sends a current, which can spin polarized current that can switch the magnetization of the free layer. In the spin orbit torque, you have a heavy metal, which such as platinum or tungsten or one of those things. Again, you send a current through this layer, then it creates what's called the spin Hall voltage that drives magnetization in the opposite direction. So this is the kind of two system they're using now to switch the magnetization. Okay, where do we use all these things? This is where you come to society, back to Earth. So we have Internet of Things, of course, everywhere. Everything needs nowadays sensing and also storage. So this all everywhere it is there. Now, if you want to have a big data storage, then of course you need magnetic random access memory because that is low power usage and also very compact. Now, of course, talking about self-driving cars and all that, there were about 30 to 50 places where the magnetic sensor was used. Now, with onset of these self-driving cars, a lot more sensors are needed. So one of the important development in the MTJ is the following. They are able to reach magnetic sensitivity using MTJ on the order of 5 times 10 to the minus 14 Tesla root hertz. Just to give a perspective, this is comparable to what's called the SQUID, yes. So superconducting quantum interference device that was used to do all this work before, like especially this magnetoencephalography. Now they can actually replace that using this magnet tunnel junction. The advantage of following: first of all, this is robust. Secondly, it doesn't need to be cooled down to liquid helium temperatures. Thirdly, this is extremely sensitive to radiation, this and that. So given all those limitations, now the onset of this MTJ can make a huge difference. They already have used this to sense the magnetoencephalography and also MEG. So this work has been published in few years ago, as you can see. This is also very valuable for a field of geology and also space application in particular. There's huge amount of demand for space application because of the robustness and non-volatility and also low power, compact, and so on and so forth. Okay, then there are other things that are also developing in the magnetic tunnel junction. For example, you can create a nano oscillator. One of the audience was talking about microwaves and generation, all that. So here is the system. It's a magnetic tunnel junction. You can actually create a spin torque into one of the magnetic layers. It can process, it can emit microwaves all the way from megahertz to gigahertz, which can be tuned with a magnetic field and a current. So these are very, very important because you can use this for interconnects. In other words, you can have communication between one device to other device in a semiconducting system as well. So we have ultra low magnetic sensors, and also we have high sensitivity microwave detectors using these magnetic tunnel junction. So detection level for these MTJs are less than a microwatt in gigahertz range. This is one of the most sensitive for detecting the microwaves. Now that is not the most important for me. But for me, it is the fact that you can use these MTJs to create what we call as neuromorphic computing system. In other words, this memory can act as synapses, what we have in a brain, and also this by changing the shape of the MTJ, you can create this oval-shaped structure that can act as what's called a spin torque nano oscillator. So this acts as a neuron. So combination of these two can be used to actually create what's called the NCS, that is a neuromorphic computing system. So we have a system where we can have a in-memory computing. This is one of the holy grail in computer system. This can do parallel processing compared to the other case where is serial processing. That's one Newman architecture. Now, another thing is with this kind of memory, you can use extremely low energy compared to the conventional hardware. That means you also have saved energy. First of all, it will be fast, it will be compact, it's all completely integrated. And thirdly, it's also using less energy, so on and so forth. So this is the kind of some of the work which is going on in other parts of the world, in particular in Europe. Now, it can also actually create a lot of these electronic components, actually, MTJs. As you see here, it can have memory, of course, comparators, sensors, so on and so forth. So what's important is this kind of MTJ, you can have a completely system level integration. You can full circuit can be done using this MTJ and universal functionality. Thirdly, is you can, as I mentioned now, you can have in-memory computing. So you can see the power of MTJ. We didn't expect that when we worked on it in 1994, 95, that we reached this level. It was beyond even our imagination how far the field has moved. So as you see here, the basic research drives technology very clearly, as we all know this. So MTJs can have fantastic computer storage capacity. And as we know from the ultra high density hard drives, then you can of course have non-volatile memory, excellent field sensors, some of the best in the field totally, and could be very useful for medical field and universal functionality. You can have everything, logic, nano oscillator, rectifier, everything. You can create complete circuitry. And in fact, in the future, as one of you have mentioned, interested in the quantum computer, maybe even before that, this kind of a neuromorphic computing can be actually very valuable, be much easier to obtain compared to quantum computer. So now it's time for us to chill down. This is for the second part, and we're going to chill down to pretty low temperature. We are talking about minus 269 degrees C, 4 Kelvin. So it's all going to be liquid helium based. And our work now I'm going to talk about is in all cryogenics and superconductors. This is the second part of the talk. How this already we know MTJs has driven the industry, driven the technology to unimaginable high level. Now let's see where this might be able to take us. Talking about superconductors, this is one of the most interesting discoveries of all time in physics. For example, superconductors are those things which are materials, common materials such as lead, indium, vanadium, niobium, or some other alloys, and so on. When you cool them down to certain temperature, below the temperature, they completely lose the resistance. That's one property of that. The second thing is, if a magnetic field is applied before you cool down, then while you cool down below the TC of the material, it completely expels the flux. It creates what's called the Meissner current. It actually creates a field flux which is opposing the applied flux. So as a result of that, in the middle, you have no magnetic field. So this can be only there up to some magnetic field. Beyond that, of course, it becomes normal. So these are some of the hallmark properties of the superconductor. Now, one more thing is these superconductor, make a wire of that, can carry current up to some point. Beyond that certain current, this can become normal. This is called critical current. This is what we're going to drive us for the next part of my talk. In other words, a superconductor supports a finite current up to the critical current, we call it JC. Let's say if you take a wire of superconductor, you send the current from right to left or left to right, it should make no difference. That's what one thinks about. But for some means, let's say by some means, you are able to actually make it uneven. In other words, critical current in one direction much different from the critical current in the other direction. If you can do that, that is JC plus in one direction is different from JC minus. This is what called the non-reciprocal current flow. That is what is superconducting diode. Superconducting diodes are nothing but non-reciprocal conductors. Now, there are also, of course, I should tell you the materials which have actually found a lot of technological application, that is high TC superconductors, YBCO, bismuth compounds, and so on and so forth. They can superconduct above 90 Kelvin actually. So there are other discoveries as well. Now, let's look at the energy usage. We were talking about energy earlier. So all those, why we need to generate power and ourselves and then sustain and put it back to the grid and all that. Now look at this chart. The green one is what the data center uses. So you can see the growth of the energy usage in the data centers. Right now it's about 6% of the average production of the power. Now in 10 years, it's going to go more than 10%. So that means we are going to be using 1000 terawatt energy just for these data centers. It could be even bigger than that because of the AI, the demand is much bigger. So we need systems which with increased power efficiency, which is for sure. So that's when we think about superconducting materials and how we can develop this into superconducting computer and so on and so forth. So once again, this data center I show you just to remind you again why you need to do these things. And now imagine where do we go? Now, just you don't have to even do quantum computing right now. Let's talk about just a simple superconducting electronic-based supercomputer. This is, by the way, one of you have worked in the Lincoln Lab, right? I wanted to show you this part of the slide which I got from Lincoln Lab. We had a project with the Lincoln Lab about a few months ago to develop something which I have delivered actually. So what they say is if you have 5 petaflops of computing you need, that occupies completely one big room with all the racks here, and it uses about more than 100 kilowatts of power. It's a CMOS-based one. It's a semiconductor-based one. Now, on the other hand, if you can develop this supercomputer using superconducting electronics, whole thing can be done in a rack mount. It's almost the size of the microwave, and the power used is only 1 kilowatt. Imagine that. So this is with a different scheme with using superconductors. So you can clearly see the 100-fold drop in the power usage. Our program actually is a step forward to realize this kind of dream. Now, just to give a perspective, talking about quantum computers. So there is huge amount of progress or effort has been put by Google and Microsoft and other companies. So for example, this is a picture of approximately 100 operational qubit, the system wiring system, actual processor somewhere down here. This is maintained at 10 millikelvin. So you can see the size of that. This is about a meter from here to here. That's the size for about 100 operational qubit. Now, to really make a good quantum computer, you need essentially millions. Although they're talking about by algorithm, you can bring it down to maybe 1,000 or 10,000 of them should be able to do a lot of work. Still, what I'm saying is if you want to make a very effective quantum computer, you need to have millions of qubits developed. So one of the bottlenecks is the following. One is you need cryogenic memory and logic. And second thing is you need to have on-chip power delivery. And third one is you need very good isolators for cleaner signal. That means where the signal is being produced, it should be isolated from the rest of the circuit. Otherwise, it creates a problem for the signal. So we want to address these things. That is, create non-volatile cryogenic memory, and you want to create a diode rectifier so that you can deliver the power to that. Thirdly, we actually want to see how we can do this all electrical means. So basically, our program should be able to drop the power down by 100,000 times, and size can be reduced by factor of 100 or more, and it's also easy to scale up. I'll show you why and how. So this is going to be a breakthrough in quantum technology of interest. We are not actually per se doing qubit, but we are going to help these things to be realized. So for example, that is the area where all the qubit circuits are located, let's say 20 millikelvin, 10 millikelvin. So currently what they do is they use room temperature memory, and some of the processing is done up here, whereas most of the processing down here. That means they go back and forth to retrieve part of the information. Halfway through the process, they put some information stored here and bring it back later. So each of these excursion going to create thermal energy introduced into the system. That means the stability of the signal is going to weaken. Second thing is it also creates a lot of electromagnetic noise. So these are the big problems. That's why we need cryogenic processing with a superconductor. That's why we go to superconductors. So we have a way to deliver actually power, as you see as you go along, and also we have a way to actually create memory. So this allows us to go towards superconducting based supercomputing. So it reduces, our program will reduce the electrical and thermal noise because we do everything at low temperature. And we found already that single flux quantum qubit program by a company is really excited about this whole thing because they can use this for directionality of the pulse, which actually makes a cleaner and stabler signal. And we of course saves energy and space, and it's a non-volatile memory. You can have diodes, actually rectifiers to create power. And we can also create logic circuits, which means we can do the whole processing there. So it has a high potential for all electrical operation, and also of course, as I mentioned before, in-memory computing also can be developed with this. So it's a compact, scalable, low power, high speed electronics one can develop with these things. So now what brought us to this level? This is the kind of fundamental work we have been doing before. In other words, we have been doing for decades, bringing a ferromagnetic material next to a superconductor. As I pointed out earlier, this is one of the most compatible interface. Okay, so as a result of that, there is a huge amount of rich physics in here, and there's potential for technology. One of the most important thing I want to point out at the interface, because this interaction, you can have magnetic fields locally on the order of hundreds of Tesla. Can you imagine? Without having to send any current or anything, just the presence of these two materials together at this interface, you can have a huge field. Then a lot of other physics you can do that. Let's not talk about that. But we want to talk about this Majorana. So this kind of system allowed us to actually look for these exotic Majorana zero modes, which is one of those predictions. So the second thing is allowed us to actually also create superconducting diode and rectifiers and so on and so forth. At the interface, we have what's called the interfacial exchange field. That is exchange coupling, which means the ions, magnetic ions here, interact with the charge carriers here, producing this huge amount of magnetic field. This is what was predicted way back in 63 and 66 by those scientists. Now, the prediction for the Majorana came along way back again 20 years ago, 25 years ago by Kitae. He predicted that if you have a superconductor, special superconductor under even special condition, the fermion state, that is the electron, the hole, splits into two parts. They're spatially separated from each other, as you can see these two red balls here. So it's a superconductor now. It's a one-dimensional wire, and it's all Cooper pairs inside, which are completely coupled. And this single one of the unpaired one can split into two parts here, as you see here. This is what's called the Majorana end states or Majorana pair. So you can imagine that now if you have a pair like this is always entangled. That means what happens here will be noticed by the other one. That means you cannot disturb one of them unless you disturb this one as well. So this kind of entanglement actually makes this Majorana pair immune to any kind of local perturbation. So these are well separated from each other, which could be even 1 micron apart from each other. So you can imagine how stable they can be. This is what one of those possible candidates for creating what's called the topological qubit. This could be a very important for the future to create this qubits for the quantum architecture, right? In other words, quantum computers. Okay, so this is the prediction by Patrick Lee and Henry Potter in MIT. He is a professor in MIT. In fact, so they came to us about 10 years ago that okay, we have a scheme, theoretical scheme, wherein you can actually create this, let's say 111 oriented gold nanowire. Then one should be able to see these Majorana modes at the end of the wire. If you make the wire narrow enough, these Majorana wave functions can reside or focus on those two ends. So how do you locate this? How do you find this? Then the idea was that if you can use a scanning tunneling microscope, then you can go and look for these states, special at the two ends. You should be able to see in the tunneling spectroscopy the presence of these kind of Majorana states. So that's what we set out to do. So that was way back in 2012. We started this program, and it took us a number of years, almost 8-9 years, to realize this. So the way we have realized the following: we have vanadium, which is superconductor, put this nanowire of the gold, then you can drive the gold into superconducting state. Then you have the European sulfide sitting on that. It turns out that if you spectroscopically scan the whole edge of this European sulfide island, you find that at the location of 1 and 8, in the presence of a large magnetic field, you can see the signature of these Majorana modes, these two modes. So if you look at the previous slide, you see this Majorana mode, it acts like a state. Okay, so we should be able to see in the Majorana, in the tunneling spectroscopy, these states evolving as a function of magnetic field. In zero field, of course, you don't see that state here in any location all the way around. But when you apply a critical field, then you can see the energy gap in all these places. There are no Majorana mode. And only these two locations, you can see this Majorana mode. This, of course, was later on verified by theory as well. That's exactly where they expected to see this Majorana mode. So in principle, we have attributed these two signatures to the Majorana wave function. What do we do now? So we had to take it towards this actual nanostructure. We cannot use a STM to create this huge number of qubits we need for making a quantum computer architecture. Whereas if we make a planar structure such as shown here, it's a very complex structure. This is what I'm ongoing right now. We have a program with the UC Riverside and also IBM lab in Zurich. So if you can create this kind of architecture and be able to realize the Majorana modes, then this is the starting point as a foundation for creating the qubit circuit, as you can see here. That will be the basic point for creating a topological qubit for quantum computing. So that work actually come to a halt right now in a way, because the funding is a big problem. So we are not able to pursue this one. So we are doing a very low key now, but it needs a lot of work and it's very challenging. Now let's talk about the superconducting diode. So since we had this platform already, except gold is missing here, of course, we can even add thin layer of gold. It doesn't make so much difference. This is superconductor. Then you have ferromagnetic insulator on the top. What we found was we send a current through this thing, we can actually see the non-reciprocal behavior. This kind of superconductor we call as asymmetric superconductor because the two interfaces are different. This is a very high spin orbit material, platinum, which is a heavy element, whereas European sulfide is a ferromagnetic insulator. That's what theory predicted, that if you have such a system, you should see this non-reciprocal behavior or diode effect. So just to remind you, a semiconductor diode, as shown here, has this kind of characteristic. You have a current here. In one direction, you have this large current flow with a small voltage applied. Other direction, we have very little current flow. This kind of non-reciprocal behavior is what the driving force for all the circuitry we are talking about, whether transistor or diode and so on and so forth. If you have a superconductor, let's say the current, critical current is different from in two different directions, then you should have this kind of behavior. In one direction, it goes very large critical current, other direction, very small critical current. Now, if you are able to maintain a current somewhere in the between this point and that point, somewhere here, then on the positive side, you have a zero resistance, whereas negative side, you have finite resistance. So the ratio is essentially infinity of resistance. Now, this kind of system behaves like a perfect diode. Okay. Now, that's what we see. Actually, this is our experimental data for a system such as this. We see a rectification of greater than 6, so with an efficiency of 70%. This is what we call a superconducting diode. Okay, this we published a couple of years ago. You can also make into a full wave rectifier as shown here. When you do that, each of this diode is made up of this kind of superconducting structure, and you can create the whole thing in one platform. When you do that, you can again see this rectification. And in fact, if you apply, if you have a capacitor on the way, you can actually create a DC output voltage. This is exactly what we needed for the power input to all those quantum circuits, which has a low temperature. Right now, they're using all the DC cables coming from the top to bottom. There are a lot of cables. That means the cables have become thicker and thicker as the current increases. Where here we can actually send AC current, and then it can be rectified at the bottom. Then that can supply to all these gadgets. So the rectification efficiency is very good. So what we found was this is the ideal way to actually power deliver to the quantum circuits operating at liquid helium temperature or even millikelvin range. And it can also create isolators, as I mentioned to you earlier. It can only conduct in one direction, not the other direction. In typical ongoing RSFQ qubit technology by a company in New York, and they are very interested in what we are doing. And it also turns out that these are all very valuable for dark matter detect. As a dark matter detector, we have a collaboration with UC Berkeley. Now, so that means they have a technological value for this, what we have done. Now, one of the couple of last things I want to talk to you about, non-volatile memory. So instead of one magnetic layer here, if you have your superconductor sandwiched between two magnetic layers, then you can actually create this parallel state or anti-parallel state. Either you can have resistance or zero resistance. This can be maintained in zero magnetic field, as you can see here. That means this is a non-volatile two-memory state in a superconductor. This is what we can do. So that's what gives rise to this kind of structure. And we are able to actually create this non-volatile memory state using the superconductor. It also turns out that you can do this with some other superconductor, such as vanadium. It should be possible with any superconductor. So this is what we want to develop in the future. So what we have here is a superconducting transition temperature depends on the orientation of magnetization of the two layers. So in the case of parallel case, you have a lower superconducting transition with a higher transition temperature for anti-parallel case, because the field that is seen with superconducting is enormous because of exchange field. Now you can see also this kind of behavior. This is what the memory is about. And on the right side, what I want to specifically show that we can actually use the same kind of architecture. You can either have memory or you can have the diode. Just depends on what temperature you operate at. For example, at a little bit higher temperature, somewhere in the middle here, you can have this behavior. When you go to low enough temperature, by toggling the magnetization, you can have either completely superconducting state or resistive state. So this allows us to actually have superconducting diode in zero magnetic field. Efficiency is very good. So this is all advantage. Then of course we can create all this logic circuit and all that from this. So again, once you can actually do in zero magnetic field. And this is in synergy with the superconducting supercomputer program, which is one of the ideal stepping stone for creating a more stable, more coherent quantum computing architecture. So now we are ready to implement this one. For example, all this processing happens at low temperature. The bottleneck is that power delivery to their system and memory. We have solved those things, and also it is compact and it's low power. Thirdly, it actually allows the qubit to be more stable compared to what was possible before. This is what we want.
Figured it out.
So you can see what?
Deign to bother to be.
Sorry, I think
I'm done.
we need to mute all our lines, please.
Okay, so you can see that there is a 1,000 times lower power usage and 100 times reduction in size, and it can be easily scaled up because our layers are just a double layer, triple layer, which can be produced in large wafer scale and can be patterned very easily. So we are able to already deliver. The near-term application is that you can use this for superconducting electronic-based supercomputers. That's the kind of program that's going on at the Lincoln Lab. So to summarize this part, we saw that if you exchange couple of superconductor with ferromagnetic layer, it's a very rich system with a lot of fantastic physics come out of it. You can tune the superconductivity by the interfacial exchange interact by depending on the orientation. And then you can also, of course, create all these things, Majorana bound states, you can superconductor diode, rectifier, non-volatile memory, and logic. So grand final is that I want to thank you all very much for your attention. And the future is cool as long as magnetism and superconductivity are there. So we are excited about it. And what the final statement I want to make is that basic research absolutely leads to innovation. There's no question at all. You can go to any kind of development, any technology development, you go back in years, you find that it started somewhere as a basic research. So absolutely one has to support basic research. In fact, we want to take this superconducting device texture to next level. We want to actually have a startup company which allows to deliver some of these components so that they can make the superconducting circuitry and the logic, everything much more feasible and realize quicker than what is possible otherwise. Thank you so much. These are some of the people. Of course, I cannot show 300 people here. This is some of the recent people. This is the gang which was responsible for Majorana work. In fact, scanning tunneling microscopy was done here. Initial work all done by Peng Wei. We have a collaboration with him still. And that's, of course, Patrick Lee. He has been a driving force theoretically, helping us a lot to reach our goal. And these are some of his collaborators in theory. And for the diode work, again, Patrick Lee was involved. And this is the postdoc who he just left about a month ago. He's the one actually initiated and his initial study of the superconducting diode. This is, of course, our collaborator from IBM Zurich. And that's again a theoretical collaborator, Akash Deep, and Sebastian Berger from Spain. That's it. Thank you very much.
Oh, Jagadeesh, I want to thank you so much for this. I have a number of comments to make, but let me just start with one observation. Your very last slide, in which you related the importance of research, and I've forgotten exactly what the language is, but you pointed out how important research is.
Yes.
I would love to see people from the White House today see this presentation and understand just how important H-1B visas are and how important it is to support fundamental research, because what you've presented today, I find to be a fascinating historical tour de force, historical and technical tour de force of the evolution of not only conventional electronics and devices, but also the next generation of quantum electronics, quantum devices. And that's where we're headed. And I have to admit, I'm going to have to sit down quietly with your presentation and my textbooks and try to understand exactly what you said, because much of it was way above my head. But I'll get to it. But I want to thank you because it really was a tour de force. And you talked about materials processing, about their importance in devices. You talked about something that is very dear to my heart, and that is involving undergraduates and graduates in research,
Yes.
getting
It
the
is
generation involved.
right. It is a pleasure actually. I want to inform that this year I was not actually keen on taking high school students because my number of group members now has reduced down to 2.
Yeah.
So very difficult to handle them. We need to really attend to them almost 6-8 hours a day. Otherwise
Yeah.
they're lost. So I had 5 of them. I was very reluctant, but these 5 happens to be really stars. I really enjoyed interacting with them. So much motivation drive. It's fantastic to see this younger generation with so much interest in learning,
Yeah,
doing
absolutely.
research and scientific discoveries. They're all in touch with me. They all want a reference letter and so on and so forth. It takes a lot of dedication to be with them and teach them
Sure.
and integrity of science and how to think. We make them think. We don't give them solutions because we don't know solution ourselves. We give
Yeah.
them actually state-of-the-art problems. So
Yeah.
in fact, one of the student, Catherine, she may be online. I don't know, Catherine's there or she's listening from Wuhan, China, imagine. So
Yeah.
that's the way it is actually. I have had fantastic success with these students. And as I mentioned, this Lisa Kinder is responsible for us to start the TMR thing because she was excited. It sort of rubs on to you when these kids come with so much enthusiasm, energy, they want to take risks, they want to do something, and
Yeah.
you just go along with that, everything works.
Yeah.
Lesson for people need to have
Yeah.
energy, positive attitude, and optimism and belief that you can do it. That's
Yeah.
it. Everything has a solution. Everything has a
Well, yeah. Well, I know your work is very well known to people, for example, at IBM and other places. When I talk to people about Jagadeesh Moodera, they immediately start talking about superconductor electronics and devices. And I know they're interested. I know they're aware of it. But I have to ask you an important question from a technical point of view and maybe a practical point of view. Companies like Meta and Google and OpenAI, they're all investing in these huge data centers. So, but the question I have is when would you predict that quantum computers are going to replace classical electronic computers? And when will that make this huge investment in data centers outdated? Is it really an investment they should be making, or should they be investing today in quantum computers? What's your take on that?
Oh, there's Catherine. See, saying hello to everyone. Wow.
Put you on the spot. I'm just curious.
You should show up, Catherine. Show video and everybody can see. So
Hi,
anyway, is this being recorded?
I'm in China now, so it's at night, so it's really late now for me.
Okay.
Yeah, Catherine, I think you must be unmuted. If you hold on, we'll have a question in a moment. I want to get Jagdish answers. Go ahead, Jag.
Is it being recorded?
Go ahead. I'm sorry, I missed you.
Is it being recorded, what I'm saying now?
Yes, of course.
Then I had to be very careful what I say.
Okay. That's very political. You're right.
Yeah.
Very
But yeah,
thoughtful.
you put
Okay.
me on the spot. The thing is, it's true that there are a lot of effort going on, there are a lot of progress. However, the net output hasn't been showing up as much as one expects. It's a very hard problem, without a question. As I mentioned, the stability, coherence of the qubit is a big problem. So how to maintain this state? So decoherence of the state in a qubit state is a problem. So as I pointed out in one of the slides, if you can do all the processing at low temperature, not going back and forth to room temperature, it's a big step forward. That's the reason we want to develop this electronics, show them it is there, it's possible to do this. So our work with the CQC is a company in New York. It might be a good step forward to show them how to take the next step. Currently, they're talking about 100 qubits. In fact, IBM is planning to have 1,000 qubits in a short time by 2030 or something, I think. So by 1,000 qubit, we should be able to do a lot of algorithm. That's what they say. And to do everything possible, whatever you want, then it takes millions of qubits. It takes time. So right now, they're trying to solve this decoherence problem using computer algorithm. They make many, and then some of them work. They find a way to mathematically actually rule out these artifacts. So it's a major problem. I would say maybe already they have opened up some, I think, sites, IBM, where people can use this so-called quantum computer to do some work. Yeah, he's there. But in a full-scale thing, it might take a long time. As I showed you.
I'm aware that at IBM they're developing something called Starling.
Right.
A computer, and that one of the things that's typical of the qubit technology is that quantum computers make errors, and Starling apparently has remedied the problem of has made error correction an old hat. They know how to do it.
Right.
But I'm thinking that as this progresses, and it's changing very fast, that
it is changing. Yes.
I didn't mean to put you on the spot, but I'm really quite interested in just your crystal ball judgment on this. If you were at a company like Meta today and you were deciding you're going to invest, or Microsoft, that Microsoft wants to restart 3 Mile Island, a nuclear power plant that has been offline for their exclusive use in their data centers. Now, that is a huge investment, a huge investment. And if
That's one way to go about, right? One way, the more you demand, you make the big house bigger and bigger. On the other hand, if you make more efficient thing, then you don't have to make the house huge.
yeah,
What you
yeah,
have. So that's one way to solve the problem by creating more and more energy, so that they can build bigger and bigger data center. On the other hand, if you go towards this kind of a way to solve problem, superconducting electronics, you can reduce.
yeah,
I think one schematic I showed you, where you can drop the field power usage by a factor of 100. You know, one of the computing architecture, if you can superconducting computer, simply superconducting computer, not even quantum computer, just
yeah.
superconducting computer, you can make it very small, already have a reduction on the power, 2 orders of magnitude. You can do this. So this is some of the things I think they want to look into, not just keep on building new power stations and new nuclear plants and all that.
Yeah, yeah. Okay. Now, well, let's take some other hands. I see Eddie's got a hand up. Go ahead, Eddie.
Yes, actually, your mention of Seagate brings back a lot of memories for me because we use Seagate drives at TMC.
Right.
And to be quite honest, we had one heck of a huge problem with them because it's not just simply the thin film that provides the memory, it's also the reading and so forth. And that head flying over 5 nanometers, you only need a small few bumps and you've got problems. And there used to be a lot of algorithms and complexity related to that, plus a lot of failures. Now, one of the things that happened when we went to solid state drives was that the reliability went enormously up and we didn't have these mechanical issues and the power went down. And that was, so there was a very rapid change within a couple of years from hard drives with spinning disks to solid state drives, which, you know, was easy plug and play, quite honestly. So my point is, I guess, is that as soon as you're able to develop these devices and show they're reliable, there will be a very rapid change. And so I guess the real question is, when will that happen?
Yeah.
See, for example, you saw that, right, MRAM, it just in about 10 years, it has come from megabytes to now 64 gigabytes. You can buy chip, MRAM chip. So imagine in the next generation, maybe they make 128 gigabits. You just need to have few chips. There you have 1 terabyte memory already. You know,
Yeah.
these are completely like solid state memory, but this is really stable. One thing. Second thing is very robust. It endures 10 to 15 cycles. That is not the case with any other thing. They're all like the 10 to the 8, 10 to the 9 cycles. This can withstand. That's a limit. They tested up to. They didn't even test beyond that. 10 to the power 15 cycles it can withstand. MRAM. True that, yes, it won't have moving parts. MRAM could be the one which can actually take you further. And of course, in-memory computing can actually make even bigger difference, because then the whole thing can be operated much lower power using this magnetic memory, as I showed you one of the schematics. So that's another way to do on chip, completely on chip. Everything happens, nothing moving, all electrical, which is not very far actually. It may be in another 5 years, 7 years.
Yeah.
On a physics basis, Majorana, Majorana, sorry. I always say Majorana. The Majorana states are also very interesting from a physics point of view. And
Yes.
I wondered if others are looking at these devices as ways to basically look at the fundamental physics of Majoranas.
Oh, absolutely. Because first of all, of course, there is a lot of controversy in the field. I don't know if you heard of it. So it was a big thing about 10 years ago, but now with all the skepticism, the funding has become sort of very low. So they're not very excited about it, funding agents. So we need to have someone to take risk. And as you can see, there's a promise there. You know, everything is like that, right? Any revolutionary technology, very risky. The science is very vague in the beginning. Later on, it evolves itself, shows up very nicely. So for example, just to give an idea, like superconducting diodes, initially it started as a theoretical thing. They predicted that, or want to be able to see 1 or 2% change in non-reciprocity, where they've created all kinds of things like spin orbit, exchange failure. But we found there's none of those things needed. Just a superconductor. Take a superconductor, create a little bit of asymmetry on one of the edges. That's enough. It can create this huge diode effect. Can you imagine 70% to 80% efficiency? That's amazing because, so this is completely unexpected, right? So we start somewhere. And of course, there are a lot of work in the past also, I should point out, in the 60s, which was forgotten. Now they're reinventing the whole thing. So this is how things going on. So if you want Majorana work, it's a very complex, as you can, so I showed you schematically what we want to create. It's really pushing the edge, at the edge of the nanostructure. And you're dealing with an insulator which is like a 0.8, 0.6 nanometers thick. So how difficult it is to maintain and do measurement and all that. So it takes a lot of work. It's not 1 or 2 people work. You need to have a team of people with sort of open-ended funding. Otherwise, very difficult.
International.
Yes.
Yeah.
Yes, we have to do that.
Okay. Let's go to Michael.
Oh, hello. Thank you very much for your presentation. I just wanted to comment on one element of it, which is superconductivity. And I would like to ask you if you're familiar with the work of Pays Salvatore. And he has been working with the Navy on superconductivity. He's also, along with the Navy, they're the assignee of a patent number 10144-532-B2. That was December 4th of 2018. And essentially, as I understand it, this craft is a repulsive gravity machine, and it uses superconductivity, and the way it achieves superconductivity, as I understand it in my limited knowledge, is that if you take a conductor, wrap it in an insulator, and wrap that in a conductor, and on the outer conductor, if you pulse a current through that outer conductor, the inner conductor can achieve superconductivity. Are you familiar with that work? Because if you look at the patent, it sounds quite strange.
So if you can kindly send me the reference for that through Ron or somebody, then
Sure.
I will have a look at it and see. I've not come across this, no.
Okay,
Sorry.
I'll pass that
Michael,
on.
let me just add a comment. There's a local company called American Superconductor,
Yes.
which has a major interaction with the U.S. Navy on dealing with some of their issue. I don't know if it's classified or not. In fact, American Superconductor was founded by some of my colleagues at MIT in the Material Science Department about probably 30 years ago, 1980, 85, 86, something like that. And I have in mind inviting them to speak with our group, but I haven't yet made that happen. But they're on my list, so maybe we'll come back to your question and they'll be able to answer more directly.
Yeah, it's very interesting.
Jagadeesh, I have one more question, and then we'll let you go. I always promise our speakers that we'll end by 12 noon at the latest. And I have one question. I see Wayne's hand up too, so we'll come back to Wayne. But just one moment. I'm just curious, you had an undergraduate and a high school student working with you at one point. How did you arrange that? Because I think that's wonderful, but how did you manage that?
Okay, for example, MIT has a Europe program. In fact, an extremely powerful program. It's been there for the last 40, 50 years, I think.
Yeah.
Undergraduate research opportunities program. These undergraduates, those days, it was much easier. They had a very strong interest in basic science. Now it's a little bit different. Now everybody wants to do AI related.
Yeah.
So they would come to me because of my articles were coming in the Tech Talk those days, printed form. So they're publicizing our work at the time. So they would come to me. I had one time like 5, 6 Europe students. It was difficult to keep them all occupied. High school students, there is a program in Boston University. It's called the RISE program. It's a very, very, very nicely run program. I have had students from them for about 35 years. So,
Whoa.
yes. So I've been one of the longest lasting supervisor for these high school students. That way we had about more than 200 students actually from that. So I have really enjoyed dealing with them. When they come here, we give them a lot of freedom to think, make mistakes. We don't criticize in any way. They are open to ask any question. They're open to ask any mistake. They're open to answer anything comes to their mind, like essentially. So they have to think freely. So that's what we create an atmosphere for actually like research kind of atmosphere, not regimented in any way. So
Yeah.
within a week, they pick up and they are very, very successful. And end of the program, they give a poster presentation where we really make sure they understand everything. Of course, this is way beyond the standard presentation, but nevertheless, they learn a lot. They learn a lot. In fact, last week I had a feedback from one of the students from last year. He
Yeah.
wants to continue doing research in undergraduate completely in next 4 years. Imagine he was with me last year from Texas for 6 weeks with me. This is enough to trigger them. It benefits a lot for these students.
Well, you know what? You have my loud applause for that, because I think that's really, really important to get young people engaged at the earliest possibility and to maintain their interest. I think that's fantastic. So congratulations for that.
Thank you.
I
In fact, it's fine. Within
I think Wayne will have. Go ahead. Sorry,
okay, please. Yeah.
Wayne.
Oh, from my limited knowledge of quantum computing, I'd like to make a few statements. There's no question that having superconducting components will reduce the cooling requirements in data centers for conventional computers.
Right. Right.
But my understanding of quantum computers, most of them have been built with cryogenic temperatures, and there's a fundamental reason for that. It is that to maintain the coherence of a state, for superposition state with a 0 and a 1, the longest that the coherence can be, the longest coherence lifetime is limited by the radiative decay time, spontaneous decay time from the 1 to the 0 state. And that scales with the cube of the energy spacing between the 0 and the 1 state. So you want to have a very small energy spacing between the 0 and the 1 state and the superposition state. And but when you have very small energy spacing, you're going to have a distribution where everything won't start off in the ground state. You'll have a lot of stuff in the excited state because the thermal distribution will just be such that there's a lot more excited state population when the two states are very close in energy. So you have the states must be close in energy to have a long radiative lifetime, radiative decay time. But when they're close in energy, you want everything, your initial state to be well defined and everything to be in the ground state. And in order to have that, you have to operate at cryogenic temperatures. If you're going to have a long spontaneous decay time from the 1 to the 0 state, and at the same time start off with all of your qubits in the ground state, so you know where you're starting, you know what condition you've initialized the computation in. I don't know if I made that clear.
Yeah, Wayne, thank you for that, because you answered a question that I had. I was trying to understand why, just exactly why cryogenics are so important, but you just answered it. I appreciate that. Thank you so much.
Yeah, I
Okay.
want to point out one thing is that this is with a semiconductor-based qubit being developed. This is a true, very small spacing for the energy levels.
Yeah.
On the
Yeah.
other hand, let's say talk about this gold surface state. Gold surface is very robust, 1,000 times bigger energy scale we are talking about. So we won't have to deal with such small energy excited states. So this is what we're trying to say. We have a platform here which can be even more robust, a lot more robust than what is being developed now. So we can use higher gap superconductors. So every energy scale goes up. So given that one, the qubit, if we develop with the Majorana, it will be a lot more stable and easily scalable, all those advantages we have. Of course, it's easy to say on the word, but actually doing this is another story. Nevertheless, we start with a better platform than what has been being experimented with. That's what I want to point out. Secondly, it also tells you why we need to make sure there is no perturbation coming in hitting this qubit state because the energy scales are very, very small. Any small perturbation, whether thermal or electromagnetic noise, creates
Yeah.
problem. That's what
Yeah.
we can do. We can deliver these parts so that way you don't have to go all the way to room temperature. You can do everything at low temperature.
On that note, I think we should bring this session to a close. Jagdish, I want to thank you again for a wonderful presentation.
Thank you very much.
Please extend my greetings to your wonderful wife, Geetha. I should mention that Geetha and I worked together at MIT for many years, which is how I got to know this guy. So I want to
Yes.
thank her for introducing us a long time ago. And everyone, we'll meet again in 2 weeks. Eddie will continue our conversation about AI in another dimension next time we meet. That will be on October, 10th, I think it is. Yeah. So have a good weekend, everyone. Thanks for joining us. And
Thank you very much. Thank you very much.
my
Thank
pleasure.
you.
Take care, folks. See you
Thank
again.
you.
Enjoy the birthday celebration with Caroline.
Okay, will do. Take care.
Bye.
Bye-bye.